I'm gonna try to stay. Okay, all right. Thank you very much for coming. Today I'm going to talk about a problem I've been very interested in recently. It kind of pulls together a lot of different research avenues over the years, and it's also forcing me to learn a lot, new plasma physics concepts. I'm not a plasma physicist. Um, I was a nighttime astronomer during my PhD and got into numerical modeling, but so go easy on me. But I'm also asking you to help me out here because to solve this problem, we're going to need a lot of different avenues talking to each other. Okay, so I work on solar and stellar flares. I study the optical and near ultraviolet radiation, how it's formed in the stellar atmosphere, and how we reproduce it in computer models. Today, I'm going to first give you an introduction to solar and stellar flares, talk about spaceflight a little bit because it's a good time to talk about that. And the main problem I'm going to be discussing today will be about what happens after particle acceleration in a solar flare. You get a beam of electrons. So by beam, I just mean a distribution of electrons with a power law distribution. And what happens to this beam after it's formed? Somehow it gets from its origin and high up in the solar atmosphere all the way down to the low atmosphere to initiate the flare itself. So the details of this are very interesting and very hard to explain. I'm going to talk about what I think is a breakthrough in this problem. And it's going to involve a combination of different approximations. And it will also allow us to address old problems, unresolved problems in the field. Particularly, I'm going to talk about the problem of forming the continuum radiation, the optical and ultraviolet continuum radiation, and how they could be related to these advances in transport theory. So you may have seen movies of solar flares. You've probably seen images in the press, and they're probably saturated and actually useless because they're very dramatic. But here's a nice movie of a big flare that happened in early March. And it shows really nicely what happens during a flare, some of the common characteristics of what lights up when. So I'm going to walk you through it here. Loop it. And this is a movie at 171 angstroms from the Solar Dynamics Observatory. So first you have a release of stress in the corona, and you have these parallel structures called ribbons that light up, which are close to the surface of the sun. And then later in the flare, you have these loops which light up. And this is a common pattern that we see in many flares, many solar flares. So here are the ribbon brightenings, which apparently spread apart from each other, like a forest fire spreading. And then later in the flare, you have these really dramatic loops, which apparently grow in size over time. So what we think is happening is there's an impulsive release of energy at the ribbon sites, causing them to light up. And there's an explosion at these sites, causing mass to ablate into the overlying coronal magnetic fields. Initially, this plasma, which has been ablated from the low atmosphere, is very, very hot, tens of millions of degrees. And it won't show up in this bandpass, because this bandpass is sensitive to temperatures of about 1,000,000 degrees, a little less. But over time, these flare loops cool down from tens of millions of degrees to a few million degrees, and will eventually shine in this bandpass. So we don't just observe extreme ultraviolet and X-rays. Flares occur across the electromagnetic spectrum, from the gamma rays to the radio. The gamma rays in the radio are non-thermal types of non-thermal radiation, and everything in between we think is type of thermal radiation in the flare. So at higher temperatures, for bandpasses that are sensitive to higher temperatures, you primarily see the loops. and for bandpasses that are sensitive to cooler temperatures, like 10,000 degrees, still pretty hot, but we consider it cool. You primarily see the ribbons or the foot points of these magnetic fields, which are threading the lower atmosphere. And this is an image, or this is a movie of H alpha, which is sensitive to temperatures about 10,000 degrees for this flare. So you'll just see primarily the ribbons spread apart. Okay. So it's on loop and you see this apparent motion. You can make these movies at home as well. It'll be weird.
What is the dark line?
Yeah, the dark. Okay, so yeah, this is sometimes in H alpha. I'll play that again. You see dark bands. This is these are the loops which have cooled down, and the material is actually condensing out of the loops. So it's like there's like catastrophic cooling and falling down the loops, and they happen to be absorbing rather than emitting.
What temperature is this?
10,000 degrees,
Oh.
about. So the solar flare is just one part of what we call a solar eruptive event, which consists of the flare, the burst of electromagnetic radiation, and the coronal mass ejection, which is the ejection of plasma away from the sun, which can accelerate charged particles. The kinetic energy of the coronal mass ejection actually accounts for most of the energy in the eruptive event. Of the remaining 20% that's in the flare, most of the energy is in the continuum radiation and the optical in your ultraviolet. So what you would be able to see with your eye if you were able to have the appropriate filter. And only a small fraction is in any given emission line, like H alpha or an emission line in the X-rays. The coronal mass ejection accelerates particles. When the mass magnetic field erupts, there's a shock that forms ahead of it, and at that shock, particles in the solar wind can be accelerated. Here is the CME from that solar eruptive event that I showed, and this one happened to be directed pretty much right towards us. And there are a couple of aspects that we need to pay attention to when these solar eruptive events occur, because they can affect our highly technological society. And these aspects are what we call space weather, the impacts of the sun on the planet Earth and interplanetary space. So the X-rays from the flare itself are the first thing we can see. They can ionize our ionosphere, so it affects the propagation of radio communication. And they can also puff up our atmosphere and increase satellite drag, as well as these other effects too. The high energy protons that are accelerated at the shock of the CME travel ahead of the CME. They're relativistic particles. And these are what astronauts need to pay attention to if they're going to the moon or going to Mars or on Moon or on Mars. Fortunately for us, we have a magnetic field that funnels most of these to the poles, but it can cause a large amount of ionization of the poles, and so planes might need to be rerouted. And then the coronal mass ejection itself, which you see here in a scattered light image. It will slam into our magnetic field and under certain conditions can induce currents in the ground. So power companies need to divert power away from fragile transformers if there's a big surge in current. So flares are also observed on other stars. In fact, other stars can be very prolific producers of flares. The low mass red dwarf stars are the most notorious for their flares. And in particular, the flares in the optical and near ultraviolet, which is what we call the white light collectively. This is a light curve of a very active star, an M dwarf, GJ1243. It's data from the Kepler satellite, which measures the flux in a broad band from 400 to 900 nanometers. Kepler was supposed to look for transits, but it also provided us with a lot of awesome data of magnetically active stars. So there's a low frequency modulation with a period of about 0.6 days. This is the star rotating and star spots coming in and out of view. So it's rotating really fast, 0.6 days compared to our sun, about 25 days at the equator. And this is thought to be one of the sources of the very large energy in the magnetic fields that give rise to the flares. And then the transient spikes here are the white light flares. And this flare right here, to give you a sense of scale, is comparable in total energy approximately to some of the largest flares we see on the sun. Studying flares on these low mass stars has become a very popular field of study over the last decade because of the issue of habitability. People are looking for Earth-sized planets in the habitable zones of low mass stars, including our next door neighbor, Proxima Centauri, which is a red dwarf flare star. And the effects of the flares and possibly the coronal mass ejections that happen alongside are subject of rigorous debate. What effect that has on the habitability of those planets and the effects on the atmospheres of those planets. It blows the atmospheres away, like for Mars, or whether somehow these planets are able to handle these huge doses of radiation. And there are two main effects of flares on these planets. So the habitable zone of these around these red dwarfs are very close, about a tenth of an AU. Okay, so the flux of radiation is very, very large, even for a smallish flare. People have researched this in detail, what effects could there be, and they found two really interesting effects. First is that if there are coronal mass ejections that are scaled up from the sun's coronal mass ejections, so scaled up by a factor of 100 or 1,000, according to the flare energy, then the accelerated particles, the protons from this coronal mass ejection, will basically eat away the entire ozone layer of this terrestrial-like world, this Earth-like world. So here is the ozone column depth over time. Here's the start of the simulated flare. And then for about 50 years, the ozone layer is wiped away. And without ozone, a lot of UV radiation can hit the ground. The plot on the right shows results from a laboratory experiment of what happens when the UV radiation hits the ground in the absence of an atmosphere entirely. So imagine like a Mars, really close to an M dwarf, and you have a UV flare go off. And so they simulated what would happen with the microbial population in the lab. Well, they didn't simulate; they actually irradiated a real microbial population. So like this is getting serious. Like the habitability of exoplanets is turning into a real serious field here. And what they found is that there's a very small survival fraction over time. But according to these biologists, that low level here, the steady state low level, is really important for the rebound. So they were very surprised, actually, that there was some remaining microbes in their petri dish or whatever they used, and that would be able to bounce back. So returning back to the sun, we are approaching a solar maximum. We're almost at sunspot maximum number 25. We want to know how strong this will be, how many flares we will have per month. Here is how we track the solar cycle. So the sun goes through cycles with a period of every 11 years. So every 11 years is a peak in the number of sunspots, number of flares, number of coronal mass ejections. Last solar max was pretty puny compared to the one in 2003 and before. And there have been different predictions for how strong this upcoming solar max will be. Initially, NASA predicted a very, very weak maximum, one of the weakest on record, actually. Okay, and this is their prediction, which has been shifted, actually. And then another group came along, actually this group is based in Boulder, with an entirely different prediction, an entirely different method. And they predicted this maximum would be one of the strongest ever on record. Since then, both have refined their predictions, and you can see how they line up with the data. There's a number of sunspots as of, I think, 3 weeks ago. I last pulled this down. So I don't know. I mean, is it going to be right between or either way? I think we'll learn a lot about the sun, how solar cycles, develop, and what determines the strength. Hopefully, they'll talk to each other. But this is a very, very contentious subject at conferences. Only time when people stand up and start raising their voice, really, in solar conferences. Bill Nye has a really excellent series called The End of the World is Nigh. The threat of a really large event affecting society is not zero. He has an episode on what would happen if there was a doofus, monitoring the sun, and this guy who was played by Seth MacFarlane, like fell asleep at the computer and, this eruption went off. We have lead time, okay? The flare goes off and we have about 18 hours for CME in the worst case scenario to reach us, okay? So if people are paying attention, I think we should be okay. So no promises.
Are there actually plans for that? Is someone at Excel waiting by the phone or?
I mean, they'll probably turn the power off for 50,000 people on 3 hours notice. This time we have 18 hours. We hope. I don't know. I honestly don't, know what the communication chain is there. Just, fingers crossed, and I bought my parents a power generator. That's all I can say. So now I'm going to dive a little bit deeper into what I'm actually concerned about with the flare, understanding the heating of the lower atmosphere and those ribbons that light up, deep atmospheric heating. And I'm referring to layers of the solar atmosphere. So just a little review here. Here's a temperature, structure versus height above visible surface. The photosphere is the visible surface, and then there's a temperature rise called the chromosphere, transition region, and the corona. And here's a simulation of the temperature change during a flare. And if that was all there is to it, it would be a pretty easy problem, right? But the thing is, it's not. The density dramatically changes. We no longer have hydrostatic equilibrium or anything close to it during the flare. And so that's where the problem becomes very interesting. That's when we start to ask ourselves how we can reproduce what's happening in the stratification with density. And what I'm primarily concerned about is what happens here in the chromosphere as it goes from this height to a deeper height, deeper column mass, and a higher temperature. And that's where we think the bulk of the optical and ultraviolet radiation originates from within the flare. How does the energy get there? How does it energized? Well, that's going to be the subject of the talk. But first, I want to show you some spectra of these ribbon brightenings. So we know approximately where to place a spectrograph slit because we have live magnetic field images coming down to us. And so we know where the conditions are right for a flare to occur. So we can place our spectrograph slit where we think these ribbons will form. The interface region imaging spectrograph, or IRIS, it's a NASA mission up there, has provided some awesome flare data for us, particular spectroscopy in the near ultraviolet around the magnesium-2 lines, and in the far ultraviolet around carbon-2 silicon-4 resonance lines. So here's a movie from IRIS. You'll see same behavior as before, pretty much, where you have the ribbons light up and spread apart, and then the loops get a little brighter later on. And on the right is going to be the series of spectra around the magnesium-2 lines. So here are the two magnesium-2 lines, near ultraviolet, and you'll see this is a spatial direction, and you'll see the brightenings go down with the motion of the ribbons over there. I just want you to notice a few things that are really interesting and that we want to try to explain with our models. One is that the magnesium-2 lines get really broad, they get really bright, obviously. There's a redshifted component, highly dynamic redshifted component, and then there's a enhancement across the entire range, the continuum radiation. Don't play that. You have to wait a few seconds here for it to get going. But so here's the slit right there. You can't see it very well. Okay, so it's gonna happen right here. They're broad. You can see these red shifted excursions there. And then
They're not the same type.
oh, they're not synchronized. No, I'm not that fancy. That'd be cool. Yeah. Yeah, and they're played at different rates as well.
Are these, I'm sorry, go ahead.
Hi, sorry, why the flare ribbons are spread?
Okay, yeah, so it's really an apparent spreading. It's not the energization in each foot point spreading directly to neighboring foot points. All the action is happening above in the corona, where the magnetic fields can do really what they want. And so what we think is happening is, first, the reconnection, magnetic reconnection happens very low in the atmosphere, so they're very compact loops. Okay, right there. And then as the flare progresses, the reconnection site goes higher and higher and higher, igniting larger and larger loops. So if you picture these as the foot points, it starts like this. Yeah.
So are the ribbons associated with foot points?
Yes, yeah. So we use ribbons and foot points interchangeably. Yeah, yeah. They're the foot points of these reconnected magnetic fields.
And in this chronology,
Yeah.
Where is there a relatively fast, also reconnection event on the scale that we're watching here? And does it happen before or after? Like, is this the cause or the effect?
This is the effect of it. Yeah,
Okay.
yeah. This is the effect. And then it's happening all throughout this movie, presumably, though we haven't directly ever observed it. We've observed signatures that are associated with reconnection, like outflows from some site up in the corona. But we're seeing the effect in the low atmosphere here. And that's what we want to understand, the relation between the reconnection, the particle acceleration, and the effect of flare.
So the reconnection happens in the loop, and then
Right,
particles fall to the.
right. Right, yeah,
Oh.
yeah, I'm gonna go with that, right, I think in the next slide here, I wanted to, we have cartoons to explain what's going on. Lots of great cartoons. So this is by, Professor, Masha Kozachenko, who has the same position as me, actually. I really like this cartoon. So here are the flare ribbons, and we're looking at the side now. And there is a twisted flux rope here, which evolves into the CME when it can erupt, okay? Under the erupting flux rope, filament eruption, magnetic fields can reconnect. Oppositely directed field lines come together and they reconnect here. And then there's a retraction from the reconnection point in both directions. And it's in that retraction process where we think most of the magnetic energy is actually released into particles, to particle acceleration. So here's a nice zoom in. Professor G actually showed this in his seminar a few weeks, a month ago or something like that. This is an awesome diagram. Here's where the reconnection happens, and it's just illustrating the different types of particle acceleration that can occur. Betatron, parallel electric fields, and Fermi acceleration. There have been some really exciting advances in reproducing the acceleration of particles and solar eruptive events from the simulations of Arnold et al. 2021. Before this, it hasn't been possible to produce a power law of electrons over several orders of magnitude. Okay, they wouldn't get a power law tail that extended way out. Here's the number versus the energy. They would just get something like this, but in these simulations, they've actually reproduced a really nice power law over several decades in energy, which is very exciting. Something to note here is that a large fraction of the background can be accelerated into these power laws or beams of electrons. And so this will relate to some of the interesting aspects of the problem I'm about to introduce, which is the following. Once these power laws are produced in the corona, okay, so high above the chromosphere, how do they get down to the low atmosphere to cause the flare brightenings in the ribbons? Well, first they will spiral along magnetic fields. Okay, they'll gyrate and they'll emit gyrosynchrotron radiation. right? So we know there are accelerated particles in the corona because we do observe this radio emission. And then once they get down to the low dense chromosphere, there are two collisional effects that occur, which I'm going to go through in the next slide. But the main reason that we think there are accelerated particles that hit the actual chromosphere is that we observe hard X-ray Bremsstrahlung radiation. So what physicists would probably call gamma rays, we call it the hard X-rays, and this produces a power law spectrum in the hard X-rays. And so we can go from the power law spectrum in the hard X-rays and with some assumptions about what happened to the electrons as they propagated down the loop, we can actually infer properties of the power law of the accelerated particles themselves. And the main technique that has been used for about over 50 years now is called the collisional cold target model. Okay, what everyone uses. But we've always known there are some severe problems with this. And I'm going to talk about one of the main problems and a possible solution today. Let's consider in a little more detail what happens right after the beam is produced. Okay, the electron beam, so produced up here in the reconnection, near the reconnection site, it will travel down the loops, okay? But it will actually travel ahead of the protons. Okay, so you have a charge displacement, an electric field. Because the electrons, if they're energized equally, the electrons go faster. So we have this electric field. And recent high spatial resolution images of the foot points, okay, give us an area, which when combined with the total power in the electrons in these foot points, give us an energy flux that we assume is produced in the corona and precipitates to the low atmosphere. So we measure the areas from the optical. Here are the contours showing the hard X-ray, so where the beams are producing Bremsstrahlung radiation as they slam in to the chromosphere and heat it as well. All right, so we can get an energy flux density. And the values we've gotten recently, well, this paper here, a very, very famous paper, are 10 to 12 to 10 to 13 ergs per second per square centimeter, above some fiducial low value that we have to assume exists, okay, about 20 keV, 10 keV. This is an enormous flux of energy, way higher than what groups have assumed to be in these electron beams over the past decades, way higher, okay? So I've already mentioned, this electric field that is produced. If you consider the electric field that's produced by this current density, it's so strong that it will stop the beam itself right away. So right when the beam's accelerated, it'll actually get decelerated by this electric field, right? It'll be stopped in its tracks. Okay. All the energy will go into the corona as thermal energy. It'll be thermally conducted down to the foot points. And we should see only thermal radiation at the foot points. But this is not the case. These contours here are definitively non-thermal radiation, okay? Somehow these high beam density power laws get down, okay, travel through the corona. You can also have all sorts of beam instability or plasma instabilities with these large electric fields. Bunemann instability is the main one that people are concerned about because these currents are so large. Here's just a quick overview of the two types of collisional processes between the beam and the ambient plasma. The high energy electrons deposit most of their energy through Coulomb collisions, causing heating. That actually is what causes the flare itself in the low atmosphere. Okay. This happens through electron-electron collisions. A beam electron collides with an ambient proton, and that's what produces the hard X-ray Bremsstrahlung. So these are the two types of collisional processes. So we have many electrons with different energies as a power law distribution. How do we solve for the evolution of this distribution? Well, we have to, there are a couple of possible methods. And the main method that we actually use is we solve for the evolution distribution function. So just the collisional Boltzmann equation here, the time evolution of the particle distribution function, the spatial divergence, the momentum divergence, and then this is the collision term, which is all important for generating the actual heating. Okay. And there are a couple ways of solving for this here. One is through the Fokker-Planck solution. But there are also some analytic solutions to this, making some approximations that actually give a pretty good estimate of the beam heating. So it can be as advanced or relatively simple as you want it to be, really depending on how fancy you want to get with the time evolution and the external forces here. So the external forces could be something like the magnetic field, causing the particles to gyrate, and then when they go into converging field, they'll bounce. Magnetic mirror, so things like that. Also, the external field could be this electric field I've been talking about when the beam goes ahead of the protons. So here is.
Sorry, when you say that, are you saying that this is such a transient phenomenon that it's short compared with like the proton travel time?
Yeah, right. There's additional evidence that adds fuel to the fire is that there have been images of the proton impact sites, the gamma rays. Okay, they produce these nuclear excitation lines, all sorts of really interesting spectral features in the gamma rays. 511 keV line is produced through the proton impact through pion decay. So we've actually seen that the foot points of the gamma rays are displaced from the electron foot points. So not only are they lagging them, they're actually being accelerated in different regions of the flare for some reason. It's an unsolved problem. So we think the electrons and protons are like almost completely decoupled for some reason. So here's just the evolution of the electron distribution with Coulomb collisions only. I don't know if I would do it. It's not a movie. No. So here's the initial, it's a Maxwellian plus a power law. And then over time, the lowest energy electrons will be depleted the fastest because the cross section is 1 over e squared. And the highest energy electrons can survive for quite a while without losing a significant fraction of their energy. Okay. So that's just to show you what collisional loss only looks like. So we can solve for the full distribution function, everything that I showed you, but we can't in 3D with time dependence. We just can't. We have to make approximations. So there are 3 classes of approximations that can be made, I guess. One is that we forget collisions entirely. We have a collisionless solution, just Vlasov-Maxwell equation. Related to this type is particle and cell. So I'm not completely clear in my mind yet how those two are different. I know they're different, but they're different. But we're limited to short temporal and spatial scales. We can follow the time evolution though, which is great. Another possibility is we can forget about the time evolution entirely. Okay, so what's the steady state solution to the distribution function in the presence of Coulomb collisions right here? And when we make this approximation, we're also able to stick this solution into a hydrodynamic code and model the evolution of the flows and the temperature and the radiation as well. Okay. And then there is a novel solution which keeps the time dependence, keeps an approximation to the collision term, but forgets the spatial divergence, and models also the evolution of background plasma waves. And this uses the quasi-linear weak turbulence theory, which I'm going to talk about how it resolves, well, is one resolution to this transport problem. So if we go back here, we solve this. We don't have a flare. I just want to point out that we actually need a heating rate in the atmosphere. So we take the gradient of the distribution, the integrated distribution function, to get Q beam, or just a heating rate, we stick in an energy equation and a hydrodynamic code to follow the evolution. Okay. So method 2 was to take away the time dependence of the beam distribution function. Include Coulomb collisions accurately. Include spatial gradient, include external forces, and then stick the Q beam into hydrodynamic simulation. And we use the radian code to do this. So it's 1D, the flows are aligned along the magnetic field, and it's been modified over decades to simulate flares better and better. And this shows you the beam heating rate here at the red curve, and then the evolution of the temperature. So initially you'll see the transition region here in the chromosphere, and they'll both be pushed inwards by the heating. This is just one simulation that we've run here. Okay, so the beam heating spikes at the top of the chromosphere, and it pushes the transition region deeper, deeper, deeper. In the bottom, we have the evolution of the gas density. So I said the gas density gets rearranged, and for that reason that flares are hard to explain. Well, here we have this high spike in gas density that's flowing down towards the chromosphere. This is the result of a strong thermal pressure gradient, a shock of sorts here, which causes material to pile up in like a little accretion plug, about 10 times the pre-flow density. And as our hypothesis is that that's where all the optical and ultraviolet radiation actually comes from.
What are the arrows?
Oh, those are the flows.
Ah.
Yeah, so we have upflows and downflows. Okay, I now want to talk about option C though, which is including the time dependence of the distribution function, but also considering the evolution of the energy density and Langmuir and ion acoustic waves. The simulation I showed you does not include that. It just includes, it basically decouples the beam distribution function from the atmosphere, calculates the beam distribution function, with df dt equals 0, and then plugs that into the code. Okay, so they're kind of decoupled in some ways. Okay, but here, this method follows the evolution of the distribution function. So the initial distribution function is a Maxwellian plus a power law. Okay, and the equation for the evolution of distribution function is as follows. Well, it includes a term to account for collisional loss, which turns out to be very important, and the resulting evolution of plasma waves. Here's a term that describes the evolution of Langmuir waves. Okay, and then the evolution of Langmuir wave energy density is given by this equation. And what happens is you have a bump on tail instability that forms because the lowest energy electron from the beam lose their energy via Coulomb collisions the fastest. Okay, so you have a dFdB that's positive, which changes the Langmuir wave energy density, which then changes the evolution of the. So it's a a coupled problem here. Other terms are refraction of Langmuir waves. This is for myself. I need to keep track of this because this is not my specialty. You have stimulated emission and collisional damping of Langmuir waves, spontaneous emission of Langmuir waves, and then critically. So the first critical ingredient was actually including Coulomb collisions, okay, to start the instability. The other critical ingredient was wave-wave interactions. Langmuir waves can decay into another Langmuir wave and an ion acoustic wave. Why is that important? Well, you have linear and nonlinear wave processes. This is a type of nonlinear wave process where the wave numbers add or subtract. And when you have this decay of a Langmuir wave into another Langmuir wave and an ion sun wave, what happens over time is you have a net accrual of Langmuir waves at smaller and smaller angular wave number k, larger spatial scale, and larger phase velocity. I just want to point out, it's pretty interesting that some of the same physics seems to be used in explaining the power spectra of ocean waves, which I've become randomly interested in. And this is, of course, one of the Nobel Prize winners, 2021. I don't know if there's a solid connection here, but pretty interesting. So here's what happens when a Langmuir wave goes to higher phase velocity. I just made this to explain to myself what happens. So we have a low phase velocity, a high phase velocity, and here's an electron, high energy electron, that is now can be resonantly accelerated. Okay. So K changes smoothly through diffusion or refraction, but it can change semi-abruptly through this decay. And higher phase velocity means it can catch up with higher energy electrons and accelerate them further. What you have is a process called self-acceleration. Here are some results from Kontar et al. 2012. These are like the final results and the results that I have become extremely fascinated with. So when they included the wave-wave interactions and Coulomb collisions, they found the evolution of the distribution functions as follows. First, it starts out as a power law. You have a depletion of low energy electrons, generation of Langmuir waves. Langmuir waves decay, can scatter, and they can result in an acceleration of high energy electrons. So we have a larger high energy tail than before, which is incredible to me. This has not been appreciated in my field, I think, very much. Here is the evolution of the Langmuir wave energy. Initially, it's like this is the wave number, and you can see the accrual of small wave number as time goes on. Here are different beam predictions after 1 second. We have the initial beam distribution function versus energy. So the electrons stand from 10 keV to hundreds of keV. This is for Coulomb collisions only, as expected. We only have loss of particles from the distribution. And this is with the nonlinear wave interactions. We have this order of magnitude increase with the highest energies, which I find extremely exciting for the following reasons. Well, first I want to show you, I actually got a hold of this code. He let me play around with it, and I'm really fascinated by it and run some new simulations. And this is the beam flux evolution for two different beam densities. This is 1% of the background density, and this is 10%. And you can just see, what happens here. We have the depletion and then an increase. Interesting thing is, like, this is, at the frontier, I think. We're getting up to mildly relativistic energies. A relativistic theory, to my knowledge, does not exist. Okay, so what I did is I'm like, okay, well, the beam, this theory says the beams should not just, get stopped in their tracks, but actually, when you consider some of the details over longer timescales than what fixed simulations are accessible to, you see the beam does get down. In fact, it gets down in a highly modified form with this enhancement at high energy. And so what I asked myself is, if you take this standard beam power law and you take his modified beam distribution, I asked myself, what kind of heating rates do I expect in the chromosphere as a result of these two different beam distributions? And so here on the right is a chromosphere, model chromosphere. You see, I have a photosphere, model chromosphere, transition region, and then corona. This is the heating rate for the standard beam distribution. It's exactly what we'd expect. A lot of heating in the high chromosphere. And then this is the heating rate for the modified beam. This is in column mass. This is difference in 2 orders of magnitude in column mass. So that's a huge amount. That's much deeper. Okay, even though it doesn't look deeper here compared to the photosphere, it's a factor of 100 higher in density. And so then it was a matter of, okay, so do we have observations that can discriminate between these two sets of heating formulations? So we use the radiant code. We simulate the evolution of the atmosphere in response to these different heating types. And it turns out they give dramatically different predictions for the continuum spectrum in the optical and ultraviolet. Let me go back real quick. So if you heat this here to 10,000 degrees, you'll produce an optically thin recombination spectrum, large Balmer jump, recombination edges. If you heat this column mass to 10,000 degrees, you'll produce a spectrum that's a lot more like a 10,000 K blackbody. And that's what we show here with an actual radiative hydrodynamic simulation. This is a spectrum that comes out. Here's the optical, here's the ultraviolet, here's the Balmer jump. This is what happens when you produce heating in the high chromosphere to 10,000 K. All right, and then this is what happens when you heat the deeper column masses to 10,000 K. It's a much smaller Balmer jump, a peak in the near ultraviolet instead of at the head of the Balmer jump here, and a dramatically different slope. But I haven't mentioned what this solves. I mean, what do we actually observe? Well, I skipped over a lot of groups research here. I'm going to summarize what we observed from stellar flares in one slide. We can take high cadence observations of flares in other stars that reliably flare. So we can stare at the star over a course of a night, get data, reliably get a flare. Okay, we're not stuck with nothing at the end. Here's a light curve in the blue of a giant flare in the star YZCMI, increasing the blue flux by a factor of almost 8. And then this is another flare, increasing the flux by a factor of 30. This is the flux from the entire star, okay, the blue flux. It's pretty remarkable. We can take measurements in different bands across the optical and fit a blackbody to it to get a color temperature. And that's what's shown on the right axis. What you'll notice is that in the rise and the peak phase, you get temperatures of about 10,000 K to 11,000 K. The spectrum that results from heating high in the chromosphere produces a color temperature of around 5,500 K. So right here. This is a long-standing problem that we've always wanted to explain, is how do you get these high color temperatures in the optical? But the spectrum that is produced from heating deep in the chromosphere gives a color temperature of 10,000 to 11,000. So it's exactly what we need to start to explain the optical observations of M-dwarf flares, stellar flares. Okay, nothing new here. This is just a very high time resolution view of this phenomenon. We can turn our attention back to the sun, to this image here, from which these very high beam flux densities are inferred when combined with hard X-rays. And we can ask ourselves if this new treatment of the beam, this new type of heating rate in the low atmosphere, actually resolves some of the problems surrounding these observations. So we can measure the brightness of each pixel at 430 nanometers. We calculate the histogram, that's the black histogram in the flare. We convert that to a brightness temperature, goes up to about 6,800 K. We can take radian, calculate a simulation with heating from one of those standard beams, standard power law beams of some given energy flux. Okay, only 5 times 10 to the 11 here, actually, not 10 to the 12, factor of 2 lower than the observations imply, but still pretty high. And we get a brightness of about here. So not able to explain the brightest pixels during there. We take the same energy in one of these new beam distributions, a Kontar beam, calling it. Same energy, we get a much brighter chromosphere, which is very exciting because we can now lower the total energy in the beam, not worry about these beam instabilities, not worry about, you know, the return current electric fields and things like that. And we can explain the brightest pixels and solar flare hook points now with lower energy in the beam. Kontar actually, he hypothesized that his new beam distribution resolves the problem with the hard X-rays as well, because these high energy electrons, as they're getting accelerated, they're emitting hard X-rays. Okay, then they get accelerated, emitting hard X-rays. So it's like for the same number of electrons, you can produce more hard X-ray radiation, which would effectively resolve all the problems associated with this observation here. I want to skip over that. How we think this all ties, well, how I hypothesize in some silly cartoon, how this all fits together. We have reconnection up here. The beams are produced they gyrate in the magnetic fields, and as the fields retract, well, they'll first get trapped here and bounce back and forth because their loss cone is not very wide yet. As the fields retract, the loss cone opens, and eventually they'll be able to escape from the foot points. And it's this region where we have the time, on the order of a second for the beam to experience this self-acceleration effect. Future work, desperately need a new particle in cell simulation. Why? Well, if you look at the literature in detail, as I have done about maybe 14 times, and try to figure out the whole story, you get a conflicting story. We still need to know how fast the self-acceleration occurs in comparison to beam instabilities, namely the Bunneman instability. Okay. This is a very short time scale, and there are different results depending on which paper you read. So this series of paper considers a very high density beam and gets this Bunneman instability and completely confines the particles where they're formed. Liam Buchner has a very high beam instability. They consider a drifting hot Maxwellian. They find that actually magnetic fields are really important, and the resulting instability criteria. The ion acoustic instability is not allowed here because I guess these modes go off to the side, and the magnetic field lines kind of like they confine everything along an axis. But what happens is the drifting hot Maxwellian gets hotter and hotter and hotter. So is this a beam being formed, or is it just thermalization? I do not know. Depending on who you ask, certain people really want this idea of a beam being produced in the corona to fail. Groups have said beams aren't produced there at all. It's like the aurora. You have Alfvén waves, which travel down to the chromosphere, accelerate particles there. Okay. But so you can interpret this in different ways, for or against the existence of beams in the corona. And then this paper here did show this acceleration effect, but they considered only a monoenergetic beam. We need a power law. And then, so this is what I think we need. We need a lower beam density than these simulations. We need a power law distribution initially, a spatial gradient for Langmuir waves to refract and diffuse. We need a confining B field, and we need 3 wave decay. Not much to ask for, right? So this is what I tentatively propose to do during my sabbatical, if I get sabbatical, is to learn a new skill here. But there are experts here who might be able to do this on a much shorter time scale, or if they're interested and have time, or it would be awesome. Here is just a result from one of the fixed simulations where we have the initial. This is a 3D fixed simulation with, I think it's Epoch, not sure exactly. They didn't state the name of the code in the paper. But here's the initial distribution. It's drifting in the opposite direction initially. They have to start it out that way. And this is their monoenergetic beam, okay? But over time, you can see that there's about 30% of the electrons that are higher than the initial beam energy. This is the self-acceleration. I think it's awesome. So in this simulation, the Bunneman instability does not develop fast enough to stop this from happening. I just want to point out that there's some really interesting synergies with other areas of physics. Flares around black holes. For example, Psi J star. Here's an X-ray flare around Psi J star, and similar processes to solar eruptions are often invoked. This is actually the Lynn-Forbes solar loss of equilibrium model stuck in a accretion disk around a black hole. I mean, and from what I've searched, this is like what most people are considering, most groups. I don't know, there might be other more valid approaches, but or more valid hypotheses, but this is one of the main hypotheses, that reconnection happens in the accretion disk. I guess makes sense. There's a lot of shear and magnetic fields. Okay. Yeah, the flares are much more energetic than stellar and solar flares. Here is, I should say, guess which model is from the sun. You probably have a hard time figuring it out, right? This is a solar eruptive model showing the reconnection here, plasmoids forming. This is reconnection and plasmoid formation in the neutron star magnetosphere. And here is a recent simulation of flow around a black hole where they have plasmoids and reconnection, things like that, X points. Similar physics across the universe. I think there's some really awesome synergies to work on. Yeah, let's skip over that. Okay, so I guess I want to close with, there's this new theory of beam transport through the corona. It predicts an evolution and the accelerated particles that is much different than if you consider just collisions or just electric fields that develop in instabilities. Okay, it actually works in the opposite direction. It accelerates particles. So there's energy loss and there's energy gain in a different part of the distribution. Total energy stay the same. And before, these high energy electrons were never really appreciated in stellar flares because of the power law distribution. Most of the electrons are at low energy, around 20 keV. And so these electrons are energetically insignificant, or at least they were thought to be. But with the Kontar transport model, it produces many more high energy electrons. And it turns out these high energy electrons are exactly what we need to heat deeper into the chromosphere, where we think we need to heat to 10,000 K to produce stellar flare observations. So yeah, I think I'll end there. Yeah, I'm going to first talk about this work at a solar conference in front of the high energy community, in front of the CTTM community in July. I mean, we've known about the Kontar work for 12 years now, but like for some reason it wasn't ever picked up or progressed further. So yeah, wish me luck with that.
Thank you.